Hello, everybody. My name is Masood Olia, and I'm a faculty in School of Engineering at Wentworth University. And I'm here with a video related to the subject of statics and to the topics of three-dimensional rigid body equilibrium. This topic usually some students have tough time with. And this problem that I'm about to show you, it's a very basic problem actually to show you just the concept and the concept of how you can balance forces or balance moment or torques. Okay, so here you have this bent pipe ABC. You could see that it's supported by three bearings basically at A, B, and C. And the objective here is to find the reactions developed at A, B, and C. So this requires obviously drawing a free body diagram. And the only force, by the way, that is acting on this is just this 450 Newton force. So let me just remove these things. Okay, so the question is, what about forces or moment reactions developed at these different bearings? So notice that at A, for example, you see this pipe is free to move along the x-axis. So just thinking of in terms of the, sorry, let me just use a different color here. So in terms of just showing you the force reaction, there must be a reaction in the y, and there must be a reaction in the z. Remember, it's free to move in the x direction. And now, let's not worry about the moment reaction. I'll talk about that in a second. What about B? Notice that the pipe going through this bearing at B is free to move along what? Along y-axis. You see that? So that leaves us what? A reaction in the x direction and a reaction in the z direction. I call it Bx and Bz. And then finally, at C, notice that this guy, the pipe, can move along potentially along the x-axis, right, along this direction. So therefore, we are left with what? A reaction in the y, I call it Cy, and then reaction in the z. And this, by the way, will give us 6 unknowns here. You see, each bearing, each support is going to give us 2 unknowns. And in general, you might say, well, what about the moment reaction? For example, at A, take a look. It's free to rotate about x-axis, let's say, but it cannot rotate about y-axis or z-axis. Well, how come we don't have moment reaction? Well, this is an example of a properly aligned system. So bearings are properly aligned. When you have properly aligned bearings, the moment reactions are 0. Okay, so you don't have to worry about any moment reactions. So we are left with 6 unknowns here, guys, as you could see. And that's actually the maximum that we could have for a problem for a 3-dimensional rigid body. Because remember, there are only 3 equations that we can use. Let's go back to black here. So the equations are what? Sum of the forces, there are 3 force equations, sum of the forces in x equals 0, in y equals 0, and in z equals 0. Right? And then we also have 3 moment equations. We can take moment about x-axis, y-axis, and z-axis, and the moment or the torque should be balanced. Of course, you can take moment about any other arbitrary axis or line that you want to, if that's going to help you with the solution. But you have 6 independent equations here, and you have 6 unknowns. So you should be okay. Now, you're not going to get into a situation that you have all these 6 unknowns coupled together in 6 equations, and then you have to create a matrix and feed it to use a program to solve for it. No, that's not the case here. And by the way, you see how they've given the x, y, and z initiating at point A right here. You don't have to use the axis there. You could move your axis anywhere you want. I mean, like if you take moment about A, about x-axis, you could take moment about x-axis at B or moment about x-axis at C. So you could move it anywhere you like. In this case, I'm not going to move it actually. I'm just going to leave it the way it is. Now, notice that if we start by, summing forces in, and I will use this equation, sum of the forces in x direction. Look, the only force that we have in the x direction is bx, nothing else. So bx must be equal to 0. So here we go. That's how easily we got bx equal to 0. Now, you don't have to do this in any order, but if you take moment about z-axis, notice that there's so many forces, the 450 that is causing all these reactions given. A sub z, B sub z, C sub z, they're all in the z direction. So it's a good idea to go ahead and take a moment about z-axis. If you go ahead and take a moment about z-axis, right, say it equals 0. Remember now, the way we calculating the moment of these forces is based on the, first of all, the direction is based on the right-hand rule. So if, for example, the tip of this pen is in this direction, if my rotation is like that, you see how my thumb is pointing in the direction of the tip of this pen. A rotation like that, about that axis is positive, but a rotation the other way, it would be negative. So that's what right-hand rule is. All right, and then we just used F times D. In this case, you don't have to use any cross product or R cross F, okay? So for example, let's take a moment about z-axis at A actually. So where the axes are actually. All right, so notice that forces that are sitting on the axis, they don't have any moment about that axis. Forces that are parallel to that axis don't have any moment. So like BZ, 450 and CY. Bx is already 0. So that only leaves you C sub y. So if you go ahead and find the moment of C sub y about z-axis, notice that C sub y times this distance, which is in this case 1, 0.4 plus 0.6. And that's it, nothing else. So look, C sub y must be equal to 0. So you already got 2 of the unknowns. That's easy, right? So unfortunately, now I have to move and see if I could make this a little bit smaller. If I could. Anyways, so now, what other equation can we use? So we've already used moment about z-axis. We got this. So let's go take moment about x-axis, for example. See if I can fit everything here. So again, we don't have to move anything. Well, axis, just leave the x-axis as z. So we take a moment about this axis of the forces. Again, AZ and AY, they are right on the axis, right? They don't have any moment. Forces that are parallel to an axis don't have any moment, or they go through the axis. So for example, first of all, Bx is 0, so it doesn't matter. Cy, you see how Cy passing through x-axis doesn't have any moment. So that leaves you actually B sub z and C sub z and the 450. So the moment of B sub z is going like this, so it's a positive based on right-hand rule. B sub z times what? B sub z times 0.6 looks like. And the moment of C sub z would be also positive. C sub z times 0.6 plus 0.6, 1.2, right? But the 450, it's going rotating in the negative direction, going like this, right? So that would be also 450 times 1.2. You could go ahead and clean this up or just leave it alone for the time being. Now, so we already took care of this. So now what about moment about y-axis? Why don't we go ahead and do this too? And that should give us another equation. And remember, again, we are not moving our axis, so it's at A. So y-axis, again, AY and AZ are sitting on the y-axis. They don't have any moment. Like CY is parallel. And by the way, CY is 0 anyway. So we might as well just remove these guys. So CY doesn't exist, BX doesn't exist. So we don't have to look at them. Taking moment about y-axis, again, these three guys have moment about y-axis. So moment of BZ about y-axis is going to be negative based on right-hand rule. BZ looks like 0.6 negative. CZ also negative. Looks like 0.4 plus 0.6, 0.4 plus 0.61, right? And then finally, 450 going positive based on rotation that it generates, right-hand rule. 450 times 0.6 equals 0. Look, two equations, two unknowns, guys. Just do a simple substitution or elimination, whatever you like. Numbers that I have here, C sub Z comes out to be 1350 newtons positive, and B sub Z becomes negative 1800. Negative means the direction is wrong. So you see how you said B sub Z is up, it's going to be downward now. Okay, but just leave them alone the way they are, and by the way, the unit is newtons. And then the last thing left, we haven't used, by the way, we didn't use this equation, sum of the forces in Y equals 0, because look, if sum of the forces in Y equals 0, the only force left in the Y direction is AY. Remember, CY became 0. So AY must be 0. So even this guy is gone. Say goodbye to this one. And then finally, the only other force we haven't calculated is A sub Z, but that comes out to be very easily determined by applying this equation, sum of the forces in the Z direction. So I have to move this up again so you can see what's going on. So you see in the Z direction, we have what? We have A sub Z. We had B sub Z. Well, in the picture, they're all positive. And C sub Z, and then 450. Remember, the other 450 here is going down, right? So plug in for C sub Z, 1350. Plug in a minus 1800 for B sub Z. And A sub Z, I believe, comes out to be a positive 900 newtons. So look, you found everything that you needed. C sub Z, B sub Z, and A sub Z, and then everything else was 0. Okay? So I hope that you like this video. As always, I appreciate it if you like my videos and subscribe to my channel. I have topics or videos, short videos that are related to different topics: statics, dynamics, mechanics of materials, system dynamics, and vibrations. Again, thank you and have a good day.